So we're going to be talking about some new world records going 23% beyond the Riemann hypothesis. So the Riemann hypothesis is one of the great problems in mathematics with $1 million prize if you solve it. But before I get ahead of myself, let's just talk about our favorite numbers, the primes. So the sequence begins just with 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. So we know by Euclid, this sequence of primes goes on forever. But famously, the primes are really known for being mysterious and having a lot of complexity. So maybe a simpler thing we could look at is just the last digit. So consider just lopping off the other digits and just considering the ones at the end. So it starts off the same for the single digit primes, 2, 3, 5, 7. And once we get to 11, we just keep the 1 at the end. 13, we just keep the 3 at the end. 17, we just keep the 7 at the end, and so on. So Brady, I'm not so fast writing all these numbers down, especially if they go on forever. Maybe with some help of a computer, maybe we can speed up this process. Let's just consider looking at the list of prime numbers up to 100. So it starts off as before, 2, 3, 5, 7. But then it goes up to 97. So that's the largest prime up to 100. So we look at the last digit of these primes. It starts off again 2, 3, 5, 7. But then at the end, when we're throwing off, we get 89 becomes a 9, 97 becomes a 7. The advantage of a computer here is that we can just change one character, and instead of looking at primes up to 100, we can look up primes to 500 and just generates that list pretty readily. And if we do the same thing, just looking at the last digit, we get this longer table of data. As a mathematician, once you see a table of data, your ears perk up and you ask, are there any patterns in this data? So Brady, maybe if we stare at this table, maybe some thoughts can emerge. Which numbers occur frequently? Are there any numbers that don't occur? You see anything?
There are no even numbers, of course, except for the 2 at the start.
And that's because?
It would be divisible by 2.
Right. So if a number ends in a 2, ends in an even number, then the whole number itself is even. By a similar argument, maybe a bit more subtle, there are no 5s in this list after the first 5. Because if a number ends in a 5, then the whole number itself has to be divisible by 5.
Same with 0.
And yeah, so 0 is a double whammy. It hits us both with being even and also being a multiple of 5. So what we've just shown here by this argument is that we only have a few options here for the digits that can appear in this list. So after the single digit numbers, eventually it's either going to be a 1 or a 3 or a 7 or a 9. And here, the point that you've just figured out is that the number 10, the base, is equal to 2 times 5. So we've just eliminated all the digits that have a 2 in it or a 5 in it.
Okay, so we got these 4 numbers. The next question I guess people ask is which are most common?
Yeah, I mean, that's the question. So a natural thing to do is maybe plot these numbers on a histogram. So let's look at the numbers up to 100 and look at the digits. So as we said before, there's going to be only one instance of a 2. In this, and we put them into bins, say one instance of a 2. Similarly, there's going to be one instance of a 5. And all the other numbers up to 100 are either going to have a 1, a 3, a 7, or a 9. One of the great advantages of a computer is you can just change one character again and generate a lot more data. So if we look at numbers up to 1,000, we can get these bar charts where these single entries are getting slimmer and slimmer, and these other 4 bars are getting taller and taller. And maybe if we go very far, let's say we go out to 1,000,000, we look at the primes up to 1,000,000 and look at their last digit, there's just a tiny sliver corresponding to 2, a tiny sliver corresponding to 5, and then all these other 4 options seems to be almost the same height. So roughly a 25% chance of getting a 1 as the last digit of a prime. Same for 3, same for 7, same for 9. So there's an equal chance to get any of these 4 options. That is no coincidence, Brady. This is the prime number theorem in action. We've been playing this game, this fun little game, looking at the last digit, but really we've been using the fact that we have 10 fingers on our hands, but we can look at other bases. For example, computers work in base 2. All their data is stored with 1s and 0s. So we can play the same game looking at the last digit in other bases. Let's just change one line of code. And now maybe we get something a bit less interesting here. So we get our first entry is a 0 corresponding to the prime 2. And then all the other primes have their last digit 1 in binary. So this just means that all the primes after 2 are odd. Maybe this wasn't as interesting, but the next interesting thing we could look at is maybe base 3. So we just increase by 1, and we look at the primes written in ternary and just extract the last digit. So as before, we just have a 0 corresponding, in this case, to the number 3 itself. But all other options for the primes are going to be either a 1 or a 2 for their last digit in ternary. And so this really, again, suggests why don't we play the same game? Now look in base 3, maybe the number's up to 1,000. There's going to be one number, namely 3, that has a last digit 0. But all other numbers are either going to have a 1 or a 2. And again, these are very much dominating. maybe if we go up to 1 million again, we see that the heights of these two options almost 50-50 split. And again, this is no coincidence, Brady. So you could pick your favorite base, I don't know, say 101, and you can play a similar game. You look at all the last digits of primes in base 101, let's say numbers up to 5 million, and you can get a nice roughly uniform distribution. And maybe there's a bit of wiggle room at the top, but as the numbers get larger and larger, the wiggles start to damp out, and you get this result. So Brady, this is kind of a fun illustration of one of the deep results in mathematics, the prime number theorem. So people on the channel may be familiar. In this case, the prime number theorem for arithmetic progressions, which says the last digit of a prime in any base you pick eventually tends to have an even chance. And that's, of course, unless there is some clear reason why there's a violation. So in the case of an even digit. So as long as the digit has no shared factors with the base, we expect an even spread across all options. So maybe to be a bit more precise as a mathematician, I just want to introduce some math notation. Pi of x here is the number of primes up to x, and the more precise count that we are interested in is looking at the number of primes up to x that have last digit a in base b.
Pi has nothing to do with pi.
Right, so this is one of those things where mathematicians are overloaded with notation at any time, and maybe at some point in 1700s people decided, this was a convenient letter to use for primes. The same consonant, but yeah, it's kind of a stretch. So this is the number of primes up to x that have last digit equal to a, and this is written in base b. The result of the prime number theorem tells us, in a more precise way, that each of these options for digits occur with roughly equal frequency. So for any choice of digit and base, pi of x, b comma a, we have this approximate relation that this count is asymptotic to pi of x over phi of b. So here, phi of b is the Euler phi function, which just counts, so phi of b is just counting the number of possible digits we could use. So the number of digits, a, that have no shared factors with b. So in maybe the mathematical lingo, we'd say that the GCD, the greatest common divisor of a and b, is equal to 1. Yeah, so this is a nice piece of mathematics that holds eventually, so as x gets larger. But a natural question, Brady, is maybe you're a little bit impatient and you want to know, how long do I have to wait for this to kick in, and those bars start to even out.
I mean, that depends how you define even out as well, doesn't it?
Right. I mean, so there are certainly very technical, like various levels of technicality how you want to be precise. But morally speaking, all we want to know is how long do we have to go along the number line to really start to see these numbers evening out. But we've now just, with this seemingly innocuous question, really gotten into the deep end. Think of people playing around on the shore at the beach. Maybe you go snorkeling and around some coral, but somehow you took a deep dive, and somehow you're now at the bottom of the Marianas Trench. You're at the deepest of the deep in mathematics. We've now gotten to the Riemann hypothesis. Okay, so I really want to narrow in on this key relationship in the prime number theorem, which is saying the digits really even out in their distribution among the primes. So let's give this a start here. So the Riemann hypothesis really has to do with answering the how soon question about star. So the Riemann hypothesis tells us that star will hold once we get, roughly speaking, x being larger than the base squared. So this is a key threshold. So in other words, the Riemann hypothesis, or more precisely the generalized Riemann hypothesis, says that this relationship star holds for bases b that are less than the square root of x as x tends to infinity. In other words, the prime number theorem is telling us a nice relationship that exists among primes for any base b we choose, maybe 10, maybe 3, maybe 101. But the Riemann hypothesis is really telling us that we can get the same phenomenon occurring even if we allow the size of our base to grow moderately with x, with the size of the numbers.
I've made videos about the Riemann hypothesis before, and I don't pretend to understand it.
Right.
But I've seen graphs and critical strips and all these different numbers, but I've never heard anything about the last digits of numbers or bases.
I mean, there are many ways to approach this great trench of the Riemann hypothesis. So one of the kind of links with the other perhaps more standard technical formulation of the Riemann hypothesis has to do with the zeros of the Riemann zeta function, so-called, and their placement on so-called the critical line of 1/2. And it is no coincidence that the critical line of 1/2 is the same constant of 1/2 occurring in this threshold of the square root of x. So these two relationships are intimately linked in this way.
Okay.
But I think this is, I guess, a more down-to-earth way to kind of talk about the Riemann hypothesis.
Okay.
So obviously the Riemann hypothesis is one of these kind of white whales of mathematics that is still unsolved today. But amazingly, in the 1960s, mathematicians were able to prove an average version of this result. Bombieri and Vinogradov, in 1965, they were able to show that this relationship star holds for almost all bases B. I'm meaning that this relationship holds for over 99.9% of B's up to this Riemann hypothesis range, square root of x. When I first heard about this result in my first year of grad school, I thought it was, absolutely stunning because I somehow felt like the Riemann hypothesis was, somehow unattainable and no one's really been able to say anything about it. And so I feel, almost, when I first learned about it, I was almost feeling like someone was keeping this from me. So I really feel someone should have told me about this earlier. And the way I like to think about this result, this over 99% result, maybe an analogy with cleaning tools. If you wanted to clean around the house, maybe you want to sanitize your hands, you get Purell. Or if you wanted to clean your countertop, you get Lysol. It says on the label, if you read it, cleans over 99% of germs, right? So this is the real selling point. And this is because, for work around the house, 99% of germs is really more than okay. And it's only really in kind of extreme ideal circumstances, like being in a hospital where you need a full sterile room to get that 100%. And so by the same token, as mathematicians, the Riemann hypothesis is really this kind of ideal scenario, getting a full result that we want to hold. But for most practical purposes, as a mathematician in my research, the Bombieri-Vinogradov theorem is this completely adequate substitute for a lot of applications.
I'm not having that, Jared. I'm not having that.
Why not?
Because in the infinite world of numbers,
right,
99% isn't that much. Like, there's still a lot of numbers that it doesn't work for.
That is definitely true. And obviously, this is part of the conceptual reason why we want to have a complete understanding. But in one of the kind of facets of the Riemann hypothesis is that people have proven many results with the initial caveat, assume the Riemann hypothesis then. And there were many results in the 1960s that went from a conditional hypothesis to a complete ironclad theorem once this result came out. And it turns out, in some technical settings, it is enough to just know this 99% version to get the desired end goal if you were using the Riemann hypothesis implicitly in your work.
But if they found a power, an exponent, where Fermat's last theorem broke, there was like one number out there where Andrew Wiles, this building wouldn't be named after Andrew Wiles.
Yeah. So, as a mathematician, you really want to get that complete understanding, and exceptional cases can really be important. And so this also ties in with previous things on the channel about the Siegel zeros, which are these potential real monsters trying to thwart the Riemann hypothesis. Before this, I just want to emphasize how kind of amazing I find this, because before this result, no one really knew anything. Like you couldn't really say much at all, and really taking this statistical perspective has really been leading to a flourishing in mathematical research. So this is, well, not, again, the ideal scenario, but for most practical purposes, as a working mathematician around the house, this is really kind of an important tool in the toolkit.
Okay, I believe you.
So now we get to the real beans. Once presented with this result, and if we're only looking at some of the bases and not all, a question comes up, another question. We asked how soon, but if we're only looking at some of the bases, can we go even sooner? Can we get a rate of convergence faster than what the Riemann hypothesis is predicting? So can we get bases B that are beyond this square root x barrier? So in other words, Brady, I'm asking to go beyond the Riemann hypothesis. It was remarkable results in the 1980s that actually first made a proof of concept showing we have this.
What is x again? Remind me what x actually is.
So x is the size of the numbers, the size of the primes we're going up to. So sometimes there's like 100, sometimes there's 1,000, 1,000,000, and this gets, these bar charts get more and more refined as x gets larger.
Okay.
But really the meat and potatoes of the question is, how soon?
Yeah.
Can we go even sooner?
That's how soon they start evening.
Yeah.
But how are you defining evening?
Yeah, so you can measure and, for example, look at the difference between the desired quantity and then the expected average. And then, so, in statistics, you have the concept of a mean, or the kind of the average of a distribution, and then also the variance, or the standard deviation. And so you can ask more technical questions about looking at the standard deviation. This is really what the Riemann hypothesis is all about. So this is kind of the second order question about the distribution of primes. So we have this, of course, result from 1965, which gets this Riemann hypothesis on average bound. But this was improved remarkably in the 1980s, getting exponents up to x to the 0.571. So the way to interpret this breakthrough, is we went 15% beyond the Riemann hypothesis. And this result really, for almost 40 years, was the state of the art going beyond the Riemann hypothesis until about 2 years ago, where James Maynard actually extended this result. So in 2021, he found that there were some bases that you could take all the way up to x to the 0.60. So in other words, we can go up to 20% beyond the Riemann hypothesis. So after almost a 4-decade hiatus, there's been progress on the problem by James Maynard, who fans of the channel.
He's up there somewhere.
Yeah.
The office is up there. We should have got him in here.
Yeah. And so today, I'm happy to say that we can get even further up to 0.617. In other words, we can go 23% beyond the Riemann hypothesis.
What does that mean?
So this means that there are some bases B of up to this size, going beyond the Riemann hypothesis range, for which the primes in that base have their digits being kind of nicely distributed as we would expect. So we only have to wait a shorter amount of time, 23% less time than we would expect from the Riemann hypothesis.
Before they start flattening out.
So this is kind of a savings of time in one sense. In other words, we can take more bases, and this result is holding for more base B expansions.
Do we know what any of these bases are?
So that's one of maybe the kind of aspects of this more statistical approach, is that we're looking at families of numbers. And so one of the insights, all the way going back to the Bombier-Vinogradov theorem, is that if you look at collections of numbers or families of numbers together, you can gain additional insights that might not be as apparent from looking at an individual number. So we can't necessarily pinpoint an exact B that this holds, but we can still have a family that's of a larger size. And again, maybe in an ideal scenario, we can try to prove the Riemann hypothesis, and we can prove these nice results for every single B. But in many practical applications, these kinds of results are very useful. We'd actually expect this to hold for all the bases, but that's, again, beyond so even if you prove the Riemann hypothesis, this would be a question yet beyond what we can do there. So that's maybe far off in the distance for future generations to think about. But at least from a statistical point of view, this is, I feel, making good progress.
We know that it holds for base 2, 3, 4.
Yeah, so for any individual fixed number, already the prime number theorem is telling us that we get this nice convergence. But it's only when the bases are allowed to grow moderately. We want to be able to quantify that rate of growth. So already we know, even by the Siegel-Wolfish theorem, which was proven about 100 years ago, we can allow the base to grow logarithmically, or very, very slowly with x, and not run into trouble. But really, you have to assume these very heavyweight conjectures, like the Riemann hypothesis, if you want an individual B to be growing like up to the square root of x. These kinds of results, I feel, have a very beautiful aspect where they connect. So the proof ideas that go into them connect a wide range of ideas across maybe seemingly disparate areas of math. So on the one hand, some ideas that go into this relate to modular forms, these kind of exotic objects that actually ended up playing a crucial role, for example, in Fermat's theorem, proven by Andrew Wiles, and has led to the Langlands programs. On the other hand, it uses results from algebraic geometry, more specifically the Weil bound and the Deligne bound from the so-called Riemann hypothesis for curves over finite fields, which is itself another story for another time. But I just want to convey the sense that there's a confluence of a lot of ideas coming together just to make progress on understanding the distribution of just the primes. And as just a last shout out, so I wanted to say that there seems to be a kind of nice revival in this field of studying these questions in the last maybe decade, where there before had been something of a lull. And I just wanted to shout out some people, Sari Drapeau, Joran Marikowski, Lasse Grimmelt, and Alex Pascati, who have been doing some interesting work, and we've been having a nice discussion. So it's really good to see this flourishing of this subject.